Imagine an electric car that can keep its battery alive, not just by plugging into a charger, but by capturing invisible energy traveling through the air. Signals from communication towers, broadcast transmissions, ambient electromagnetic waves constantly moving around us. It sounds like something straight out of science fiction, but a new concept tied to African inventor Maxwell Chikumbutso is sparking conversations that are making automakers around the world pause and pay attention. For decades, the electric vehicle industry has focused on the same challenge: better batteries. Tesla, BYD, Toyota, and other giants have invested billions trying to extend range, reduce charging time, and improve battery lifespan. Yet the basic principle has remained mostly the same: store energy chemically, discharge it when driving, and recharge when empty. But now, the idea being discussed in certain tech circles suggests a different path altogether. Instead of relying only on stored chemical energy, what if an EV battery could also harvest energy from radio waves in the environment? Radio waves are everywhere. Every phone call, every TV broadcast, every satellite signal, every Wi-Fi router constantly sends electromagnetic waves through the air. Normally, these signals carry information, not power. But technically, they still contain tiny amounts of energy. Scientists have long known that with the right technology, this energy can be captured. The principle behind it is something called RF energy harvesting. Small antennas called rectennas can capture radio frequency signals and convert them into electrical power. The concept isn't new. Researchers have used similar systems to power tiny sensors, low-power devices, and experimental electronics. But scaling that idea up to something large enough to help power a car battery? That's where things become far more ambitious. This is where Maxwell Chikumbutso's controversial and fascinating technology claims begin to attract attention. Supporters say his systems could capture and convert ambient electromagnetic energy, including radio waves, into usable electricity more efficiently than traditional RF harvesting methods. If such technology truly worked at scale, it could change the entire conversation about electric mobility. Imagine an EV battery that slowly replenishes itself while parked. Imagine vehicles gaining small amounts of energy simply by existing in a world filled with wireless signals. The car wouldn't rely entirely on radio waves for power, at least not in the early stages, but the concept could supplement traditional charging, extending range and reducing dependency on charging stations. And that possibility alone is enough to make engineers curious. Because the biggest barrier to mass EV adoption today isn't technology, it's infrastructure. Charging networks still struggle to keep up with demand. Long-distance travel requires planning around charging stops. Battery degradation raises long-term concerns for owners. If even a small portion of that problem could be solved by harvesting energy from the air itself, the implications would be enormous. Picture urban environments filled with electromagnetic signals, cell towers, 5G networks, satellite communication systems, radio broadcasts, and countless wireless devices. A future EV equipped with advanced RF harvesting technology might constantly collect micro amounts of energy from this invisible sea of signals. Over time, those micro amounts could accumulate. It wouldn't replace charging stations overnight, but it could reduce how often drivers need them. Some futurists even imagine parking lots that amplify this idea. Structures designed to concentrate radio frequency energy, allowing parked EVs to recharge passively without cables. It's a concept that sits somewhere between wireless charging and environmental energy harvesting. And if it worked, the entire EV ecosystem would shift. But the story becomes even more interesting when you consider the broader context surrounding Maxwell Chikumbutso himself. The Zimbabwean inventor has become one of the most debated figures in alternative energy discussions. His supporters portray him as a visionary engineer developing breakthrough technologies, from wireless power systems to unconventional electric vehicles. Critics, however, argue that many of his claims have not yet been independently verified by mainstream scientific institutions. And that tension between bold innovation and scientific skepticism is exactly why stories like this generate so much attention. Because throughout history, revolutionary technologies often started with ideas that sounded impossible. Nikola Tesla once proposed transmitting electricity wirelessly across the planet. For decades, people dismiss the idea as unrealistic. Today, billions of devices, from smartphones to wireless earbuds, depend on forms of wireless energy transfer. So when discussions emerge about EV batteries harvesting radio waves, it naturally triggers two reactions at the same time: excitement and doubt. Engineers immediately start asking questions. How efficient is the conversion process? How much energy can realistically be captured from ambient signals? Would the energy harvested be meaningful enough to impact an EV's range? Could such systems interfere with communication networks? And perhaps the biggest question of all, can this technology scale? Because capturing microwatts of power for a tiny sensor is one thing. Capturing enough energy to help power a vehicle is an entirely different challenge. Yet researchers around the world are already exploring similar directions. Universities and laboratories have been experimenting with RF energy harvesting, ambient energy systems, and wireless power transfer technologies for years. Some prototypes have successfully powered small electronics using environmental electromagnetic energy. If breakthroughs in materials, antenna design, and conversion efficiency continue, the concept could gradually move from laboratory experiments toward real-world applications. And that's where the automotive industry starts paying attention. Automakers are constantly searching for technologies that could give them an edge in the EV race. Better batteries mean longer range. Faster charging means more convenience. But self-supplementing energy systems, batteries that can partially recharge themselves from environmental sources, would represent something entirely different. It wouldn't just improve electric vehicles. It could redefine how they interact with the world around them. Imagine driving through a city where your car continuously gathers tiny amounts of energy from communication networks. Imagine highways equipped with infrastructure designed to broadcast energy signals safely for vehicles to capture. Imagine a transportation ecosystem where energy flows invisibly through the environment instead of only through cables and plugs. Suddenly, the idea of range anxiety begins to fade. And that's why even the possibility of such technology sparks conversations inside research labs and innovation departments. Because in the world of technology, sometimes the most disruptive breakthroughs don't come from improving existing systems. They come from completely rethinking how those systems work in the first place. And the idea that electric cars could someday draw power from the invisible radio waves surrounding us is exactly the kind of radical concept that keeps engineers awake at night, both excited and skeptical at the same time. Yet the deeper researchers explore ambient energy harvesting, the more questions begin to emerge, questions that could determine whether this vision becomes a real technological shift or remains an intriguing scientific experiment. Because once you start analyzing how much energy truly exists in the radio waves around us, the story becomes even more surprising and far more complex. At first glance, the world seems saturated with wireless signals. Cellular towers broadcast constantly. Satellites beam communication across continents. Wi-Fi routers fill homes, offices, and public spaces with invisible connectivity. Radio and television transmitters push signals for kilometers in every direction. But when engineers measure the actual energy inside those signals, they discover something interesting. Individually, each signal carries only a tiny amount of usable power. In many environments, the energy density of ambient radio waves is extremely small, often measured in microwatts or even nanowatts per square centimeter. That's enough to run a sensor, maybe a tiny chip, but nowhere near the power required to move a 2-ton electric vehicle down a highway. And that's where the real technological challenge begins. If a system like the one being discussed were ever to work for electric vehicles, it would require an entirely new level of efficiency in capturing and converting electromagnetic energy. Antennas would need to be far more sensitive. Rectifying circuits would need to waste almost none of the captured energy. And the battery system would have to be designed to store extremely small trickles of power continuously. Think of it less like filling a bucket with a hose and more like collecting raindrops. Each drop is tiny, but if you collect them long enough, they add up. Some engineers believe the most realistic scenario wouldn't involve powering a vehicle entirely from radio waves, but rather supplementing its battery over time. Small amounts of harvested energy could maintain charge levels while parked, power onboard electronics, or slightly extend driving range. Even a small improvement could matter. If an EV could recover just a few extra kilometers of range each day through passive energy harvesting, that could reduce the frequency of charging cycles. Over months and years, that might slightly reduce battery wear and improve long-term efficiency. And this idea doesn't exist in isolation. Around the world, researchers are exploring multiple forms of ambient energy harvesting. Solar panels integrated into vehicles are already appearing on some experimental models. These panels can generate power from sunlight to support auxiliary systems or add a little extra driving range. Some engineers are experimenting with vibration harvesting, capturing energy from the motion and movement of a car itself. Others are studying thermal energy recovery, converting heat from components into electricity. When you combine several small sources together, the cumulative effect can become surprisingly useful. And that is where the concept tied to Maxwell Chikumbutso's ideas begins to intersect with broader scientific research. Because even if the exact claims surrounding radio wave-powered EV batteries remain debated, the underlying principle, harvesting energy from the environment, is a real and growing field. In fact, many experts believe the future of electronics will depend heavily on self-sustaining energy systems. Imagine smart cities filled with sensors that never need battery replacements because they harvest energy from their surroundings. Imagine wearable devices powered by body heat or motion. Imagine infrastructure that quietly gathers energy from light, vibration, and electromagnetic waves to operate indefinitely. In that world, the line between a battery and an energy system begins to blur. And electric vehicles, which already contain some of the most advanced energy systems ever built, could eventually integrate similar ideas. But if something like radio wave energy harvesting ever became practical for EVs, it would require breakthroughs in several key areas. One of the most important would be antenna technology. To capture energy effectively, a vehicle might need specialized antenna arrays integrated into its structure. Instead of a single receiver, the car could have multiple antennas embedded into its body panels, roof, or chassis, constantly scanning and collecting electromagnetic signals from different frequencies. Another challenge would be conversion efficiency. Traditional RF harvesting systems lose a significant portion of captured energy during the conversion process. Improving this efficiency would be critical if such systems were to generate meaningful amounts of electricity. And then there's energy management. The vehicle's battery system would need intelligent software capable of collecting extremely small bursts of energy and integrating them smoothly with the primary power system. That means advanced power electronics, precise voltage regulation, and adaptive energy routing. In other words, the idea might not depend on a single breakthrough. It might depend on many smaller breakthroughs working together. And history shows that this is often how technological revolutions actually happen. Rarely does one invention change everything overnight. Instead, progress arrives step by step. A better material here, a smarter algorithm there, a more efficient circuit somewhere else, until suddenly a concept that once seemed impossible starts becoming practical. That's exactly what happened with lithium-ion batteries themselves. Decades ago, they were expensive, fragile, and impractical for large-scale transportation. But steady improvements transformed them into the backbone of the modern electric vehicle revolution. So, when unusual ideas appear, like EV batteries interacting with radio waves, engineers don't immediately dismiss them. They analyze them, they test them, they question them, and sometimes, hidden within those questions, they discover entirely new directions for innovation. For automakers competing in the global EV race, staying ahead means exploring every possibility. Companies are already investing billions into solid-state batteries, ultra-fast charging systems, and new battery chemistries designed to store more energy with less weight. But the most disruptive technologies often come from unexpected places. A small laboratory, a university research team, or an independent inventor working far from the traditional centers of automotive power. That's part of why stories surrounding Maxwell Chikumbutso attract so much attention. Whether every claim proves accurate or not, the ideas themselves push people to think differently about energy, mobility, and technology. And in innovation, Sometimes asking the right question is just as important as finding the final answer. Could electric vehicles someday harvest energy from the invisible signals filling our atmosphere? Could future batteries become hybrid systems, part storage device, part environmental energy collector? Could cities eventually become giant energy ecosystems where vehicles, infrastructure, and wireless networks interact in ways we're only beginning to imagine? These questions might sound futuristic today, but so did electric cars themselves just a few decades ago. And as the search for cleaner, smarter transportation continues, the industry may discover that the next big breakthrough isn't just about building bigger batteries. It's about discovering entirely new ways to power them. Because once engineers begin thinking about vehicles as part of a larger energy ecosystem, the entire concept of transportation starts to evolve in unexpected ways. For more than a century, cars have been simple energy machines. Fuel goes in, motion comes out. Whether it was gasoline, diesel, or electricity, the process remained largely one-directional. Energy stored in the vehicle gets consumed as the vehicle moves. But the next generation of mobility could be very different. Instead of simply using energy, vehicles may become active participants in the energy environment around them. Picture a future city where every vehicle is not just a consumer of electricity, but also a collector, manager, and distributor of energy. Cars parked in garages quietly harvesting tiny bits of power from radio signals, sunlight, temperature differences, and even vibrations in the surrounding environment. Individually, each source might be small, but together, they could create a constant trickle of energy flowing into the vehicle system. This idea begins to reshape the way engineers design batteries themselves. Traditional EV batteries are built around one main task: storing a large amount of energy and delivering it quickly when needed. But if a battery also receives continuous micro-inputs of power from environmental sources, its internal management systems would need to evolve. Instead of simply charging and discharging, the battery would be balancing multiple energy streams at once. Think of it like a reservoir fed by many tiny rivers. Some flows are strong and fast, like plugging into a charging station. Others are slow and steady, like solar panels or ambient energy harvesting. Managing those flows efficiently would require advanced software, artificial intelligence capable of predicting energy inputs, controlling power distribution, and optimizing storage cycles to extend battery life. And that's another reason the automotive industry is paying close attention to experimental energy technologies. Modern vehicles are no longer just mechanical machines. They are rolling computers filled with sensors, processors, and algorithms constantly analyzing data in real time. That digital intelligence could make it possible to integrate new forms of energy harvesting in ways that weren't possible even a decade ago. For example, imagine an EV that recognizes when it has entered a dense urban area filled with communication towers. The car's onboard system might automatically activate specialized antennas designed to capture radio frequency energy more efficiently. Later, when the vehicle moves into a rural environment with fewer wireless signals, the system might shift focus towards solar panels or kinetic energy recovery instead. The vehicle would essentially adapt to its surroundings, constantly searching for opportunities to collect energy from the environment. And suddenly, the idea of range becomes more fluid. Instead of a fixed battery capacity, range could become dynamic, changing depending on how much environmental energy the vehicle manages to gather over time. Now imagine this technology scaled across millions of vehicles. Cities could eventually develop infrastructure designed specifically to support ambient energy systems. Streetlights, communication towers, and transportation networks might be engineered not only for their primary functions, but also to contribute small amounts of harvestable energy to the vehicles moving through the environment. It would be a subtle transformation, one that most people might never even notice. But beneath the surface, a quiet exchange of energy would constantly take place. Vehicles collecting power, infrastructure broadcasting signals, networks interacting in ways that blur the line between transportation and energy distribution. This is the kind of long-term thinking that excites futurists and engineers alike. Because every major technological shift begins with a change in perspective. At one time, electricity itself was considered mysterious and impractical. At another time, wireless communications seemed impossible. Then the internet connected the entire planet. And now the automotive world is experiencing its own transformation as electric vehicles replace combustion engines. Yet even within this transition, researchers know that today's solutions may not be the final destination. Lithium batteries may dominate the market right now, but scientists are already exploring alternatives: solid-state batteries, sodium-ion cells, metal-air systems, and entirely new approaches to energy storage. Some of these technologies could dramatically increase energy density. Others might reduce costs. And a few could introduce completely new capabilities that redefine how vehicles interact with energy itself. This is where the conversation around radio wave harvesting becomes so fascinating. Even if the technology never becomes the primary power source for electric cars, it could still influence the direction of research. Sometimes the most valuable ideas are not the ones that immediately succeed, but the ones that push scientists and engineers to explore new questions. What if antennas could be embedded seamlessly into vehicle materials? What if advanced nanomaterials could capture electromagnetic energy more efficiently than current technologies? What if future communication networks, like the generations beyond 5G, were designed with energy harvesting in mind from the very beginning? Each of these questions opens doors to possibilities that don't yet exist. And innovation thrives in exactly that kind of uncertainty. Because somewhere between skepticism and curiosity lies the space where breakthroughs happen. Automakers know this well. The companies that dominate the next era of transportation won't necessarily be the ones that build the fastest cars today. They'll be the ones that understand tomorrow's energy systems first. And tomorrow's energy systems may look very different from anything we see today. Imagine a world where vehicles are constantly connected, not just through data networks, but through energy networks as well. A world where your car gathers small amounts of electricity throughout the day simply by existing within a technologically rich environment. A world where the boundaries between energy generation, storage, and usage slowly disappear. It may sound futuristic now, but the seeds of that future are already being planted in laboratories, universities, and research centers around the globe. And every once in a while, an unconventional idea, like an EV battery interacting with radio waves, reminds the world that innovation rarely follows a straight path. Sometimes it begins with a question that sounds almost impossible, a question that makes experts pause, debate, and investigate. Because hidden inside those questions might be the first hint of a technology that changes everything. And as researchers continue experimenting with ambient energy systems, wireless power transfer, and advanced battery designs, the possibility remains that the next major leap in electric mobility won't come from simply building a bigger battery. It might come from learning how to capture the invisible energy that already surrounds us every moment of every day. Because if vehicles truly learn how to interact with the invisible energy around them, the way we think about power itself may begin to change. Right now, energy feels like something we must constantly go and get. We plug in our phones. We visit fuel stations. We stop at charging points. The entire infrastructure of modern transportation revolves around the idea of traveling to a place where energy is stored. But what happens if energy slowly begins to come to the vehicle instead? Not in dramatic bursts of power, but in small, continuous flows gathered from the environment. In that world, charging may no longer be a single moment where a battery jumps from empty to full. Instead, it could become a continuous background process happening throughout the day. While parked outside an office, while waiting in traffic, even while sitting overnight in a garage. The vehicle would always be collecting something: tiny signals, scattered energy, small environmental inputs, gradually feeding them back into its system. And over time, that could fundamentally change the rhythm of electric mobility. Drivers might notice that their battery levels fall more slowly than expected. Vehicles might recover small amounts of range during normal daily routines. Fleets of taxis or delivery vehicles might reduce their charging downtime simply because their systems are constantly absorbing bits of energy from their surroundings. It wouldn't eliminate charging stations, but it could make them less critical. And when you combine this concept with the rapid progress already happening in battery technology, the picture becomes even more interesting. Solid-state batteries promise greater energy density. Ultra-fast charging technologies aim to refill EVs in minutes instead of hours. Artificial intelligence is optimizing energy usage inside modern vehicles. And experimental energy harvesting systems could add yet another layer to the evolution of electric transportation. Individually, each advancement pushes the industry forward. Together, they could reshape the entire mobility landscape. This is why the idea of a radio wave interacting battery, even if it remains controversial or experimental, captures the imagination of engineers and futurists alike. Because it challenges one of the most basic assumptions about energy, that power must always be stored before it can be used. Instead, it hints at a future where energy is constantly flowing, constantly moving, and constantly being collected from the world around us. Of course, turning such ideas into practical technology is never easy. Scientific validation, independent testing, engineering refinements, and large-scale manufacturing would all be necessary before systems like this could ever reach commercial vehicles. The automotive industry moves carefully for good reason. Safety, reliability, and efficiency must all be proven before new technologies become part of everyday transportation. But history shows that breakthroughs often begin as bold concepts that sound unusual at first. Electric cars themselves were once considered impractical curiosities. Wireless communication once seemed like an impossible dream. And today, both are essential parts of modern life. So, whether the future of EV batteries truly includes radio wave energy harvesting or not, the conversation itself reveals something important. The search for better energy solutions is far from over. Engineers, inventors, and researchers across the world are still exploring new ways to capture, store, and use power more intelligently. And somewhere among those experiments, those debates, and those unexpected ideas, the next great transformation in electric mobility may already be quietly taking shape. Maybe it will come from a new battery chemistry, maybe from revolutionary charging infrastructure, or maybe from something as invisible and overlooked as the radio waves already moving through the air around us. If that day ever arrives, the electric vehicles of the future won't just run on stored electricity. They may run on the energy of the world itself. And when that happens, the line between technology and environment will begin to blur, creating a new chapter in the story of human mobility. A chapter where cars are no longer just machines that consume energy, but intelligent systems that learn how to live within it.